Well, we're doing well. The last video we ended with this example, okay? And it is an area enclosed by two curves. We are going to continue on with finding the area between or involving two curves, but notice that this one wasn't between two curves, right? You simply had to determine where it was that you needed what the interval of what the limits of integration were and which curve you needed to use in your integrand. But when we move on, we're going to be doing some area between curves. And just to be exhaustive, what we need to do is we need to back up and just remember a simple geometric principle, which we've seen before. I mean, you've seen it in geometry, you saw it on SAT questions, because they love to ask them on the SAT. But you also saw them in earlier sections of calculus, specifically when we did the washer method, in terms of finding the volume of a revolution, right? So let's say I didn't want the area of the whole sector. I wanted the area between the curves. Well, if you wanted to find the area of the entire donut, right, the area between those circles, it's really easy. It's the whole minus the whole, right? Well, that, of course, is going to be pi big R squared minus pi small r squared. Well, when we're dealing with a sector, it's the same principle because it's just a fraction of that, right? And if this right here is theta, then the area of the sector is going to be 1/2 theta r squared minus 1/2 theta r squared. Big R, of course, referring to the big radius, and the small r referring, of course, to the small radius. This, of course, can be rewritten like this, which, of course, has implications for our integrand, because big R will just be whatever. We'll just use f of theta for whatever the outside polar equation is, and we'll use g of theta for whatever the inside is, because really what you're doing is you're basically taking the area of the whole sector and subtracting the area of the small sector. So it's still whole minus whole, okay? Now, we did this, like I said, with the washer technique, because and we've done this in a whole lot of other ways, but now let's go ahead and apply it to polar. Now let's go back to that same equation, okay, that same graph, the same two equations, and let's say I wanted to find the area between the curves in quadrant 2, okay? Well, let's go ahead and remind ourselves just visibly, right, marking off quadrant 2. Okay, and we still have to imagine the inputs sort of sweeping out like this, right, through that region. The area between the curves is going to be this whole area right here minus this little bit, this little, almost looks like a crescent, but not quite. So we are looking for that area right there. Now, we want to first designate which one is the outer, right? Well, this one right here, this curve right here is the outer, and that one is associated with this curve, right? And then we want to designate that inner curve. I don't know if you can actually in the video pick up the difference between red and the blue, but the arrows help, right? And basically that's going to be the inner curve. So what we need to do is we need to set up, and of course we know the limits of integration. They're defined by the quadrant that we're in, right? And so the limits are pi over 2 to pi. So we need 1/2 pi over 2 to pi, and then we need the outer curve squared. So that's our big R squared. and then minus r small r squared. Okay. Now, this actually does work out to be relatively straightforward in terms of calculations. Or you can do this by hand is what I'm saying. But you have to multiply it all out, and it's ugly. Okay. And what you get here is you get 1 plus 2 sine theta plus sine squared theta minus 1 minus 2 cosine theta plus cosine squared theta. And it's not too ugly, right? But it's not pretty. And what happens is this one and this one cancel out. This one, these two go together, okay? Oh, by the way, no, it's supposed to be negative. Sorry. It's supposed to be negative. Those two go together and will make negative cosine 2 theta, right? Because the sine squared and the cosine squared are reversed. And so what we need to do in order to simplify, let's put our positive term first, 2 sine theta. And then we'll go minus 2 cosine theta. Sorry, I forgot to cross those two out. And then minus cosine of 2 theta, d theta. All right, well, when we integrate, it's going to be, relatively straightforward. We'll leave the half out in front, and that becomes negative 2 cosine theta minus 2 sine theta, and then minus 1/2 sine of 2 theta. And you're going to be relatively surprised at what all of this work actually gives us. We still have the 1/2 out in front. Let's go ahead and bracket. Now when I start plugging in pi, I'm going to get, sorry, this is supposed to, 2 cosine. So negative 2 cosine pi, negative 2 sine pi, negative 1/2 sine of 2 pi. Minus negative 2 cosine pi over 2, negative 2 sine pi over 2, and negative 1/2 sine of pi. Now several of those obviously cancel out because they're 0. This is 0, this is 0, okay? This is 0, this is 0. So what you really have here is negative 2 times a negative 1, so that's positive 2. And then you have sine pi, which is 1. So this is a negative 2, but you're subtracting that negative 2. So this is going to be plus 2. So you have 1/2 times 4, or just 2. Yay! All right. Well, let's actually look at the same graph, and let's ask, how about the area between the curves in quadrant 1? Okay. Now we know where quadrant 1 is, so let's go ahead and shade the area between the curves. And what we notice is what we had sometimes when we did rectangular, right? Basically, you had to break the integral apart because, you had, like for example, if you had the area between the curves and you did that number and you were looking for the area between A and B. Well, on this portion, F is on top up to this point of intersection, but in this portion of the interval, G is on top, and therefore you had to break it up into 2 integrals. Now this one, thankfully, there's symmetry, okay? So that's going to help us a whole lot. But so let's go ahead and just deal with this portion down here, because at that point we can double it. So this is my 1 plus sine theta curve. This right here is part of my 1 plus cosine theta curve. Okay, so basically this winds up being my big R, and this winds up being my small r. Well, since I'm going to take that integral and I'm going to double it, I know that my limits of integration are going to be 0 to pi over 4, right? I've already calculated that point of intersection. You can eyeball it anyway, right? And I'm going to, and of course, from the last one, it's going to be reversed because it's going to be 1 plus cosine theta squared minus 1 plus sine theta squared d theta. Now that is the area of one of those green portions, so in order to get both of them, I'm simply going to multiply by 2. Well, since this is basically the negative of the integrand I had in the last one, I don't need to go through a whole lot of work to simplify. I can go ahead and just call it cosine 2 theta plus 2 cosine theta minus 2 sine theta, which was, of course, just the negatives of the last one. And, of course, if the integrand is the negatives, then it's going to integrate into the negatives of the last problem. Okay, and then plus 2 cosine theta. And I'm going to go from 0 to pi over 4. Now, it's not pi over 2 to pi. It's not 0 to pi over 2. You got this pi over 4, so it's not going to be quite as tidy as the last one. But you're still going to get recognizable values that you should know how to deal with. Okay, and so you're going to get 1/2 sine of pi over 2, 2 sine of pi over 4, plus 2 cosine pi over 4. Yep, that's where the radicals are going to come in. And then 1/2 sine of 0 plus 2 sine of 0 plus 2 cosine of 0. And that right there is your big F of B minus big F of A. Now, of course, there are still a couple that cancel out on this one, and that's going to be, oh, sorry, I put thetas instead of zeros. Sorry, it's just a habit. Okay, 0. So that goes away, that goes away. This is 1/2 sine of pi over 2. Well, sine of pi over 2 is 1, and 1/2 of that, of course, is just going to be 1/2. This winds up being root 2 over 2 times 2, so it's just root 2. This winds up being the same thing. And this over here, of course, is cosine of 0, which is 1, so it's minus 2. So really what you have here is 2 root 2 minus 3/2. And 2 root 2, of course, is like 2.828 basically. And then minus 1.5 is going to be 1.328. And that is the area of both of those green shaded sections. Okay. Now, I know that I said we were going to do only one more area problem in this particular one, but between making of video 2 and making of video 3, I changed my mind. So this is the problem that I was actually going to talk to you about. Now that we've gotten some of the rudimentary problems with area between the curves done, let's go ahead and do this one. And this one is a little bit more challenging, and I'll explain why here in just a moment. Now we need to find the area of the region enclosed by the circle and a petal of the curve. So what we're looking for is this pink region right here, okay? Now, there's also this portion right here, the rest of the petal. Now, the problem is, it doesn't seem like it's going to be the area between curves because you're looking for this area and not this area. But you can't actually find this area with a single integral, okay? And I'll explain why if you can't see it, I'll explain why in just a moment. But if this region and this region, let's name them. So this is region, okay, 1, and this is region 2. The area of region 1, is the area of the petal, like of the entire petal, minus the area of region 2, okay? And that's how we're going to go about finding this particular area. I'll show you another way to do it here before long, but the first thing we need to do, of course, is find those points of intersection, right? The points of intersection here and the points of intersection here. Now you should know the limits of integration of the entire petal, but we'll get back to that, okay? So I need to find the points of intersection, and that's real easy because r is equal to cosine 3 theta and r is equal to 1/2. So really what I'm looking for is cosine of 3 theta. Where is that 1/2? All right, well, cosine of 3 theta is equal to 1/2, where that angle measurement is either pi over 3 plus 2 pi n, or that angle measurement is negative pi over 3 plus 2 pi n. That means that theta is equal to pi over 9 plus 2 pi over 3 n, and theta is equal to negative pi over 9 plus 2 pi over 3 n. Now that means that these are going to be our limits of integration. Okay. If we were using one of the other petals, of course, we would use the plus 2 pi n in order to get those, okay? So this is negative pi over 9. This is negative pi over 9 plus 2 pi over 3, right? This is pi over 9. This is pi over 9 plus 2 pi over 3, and on and on and on and on and on. Now, that means that what we're doing here is we're using the limits of integration of negative pi over 9 to pi over 9, or basically we just need to recognize that those are the limits of integration. Now, if we want to find the area of the petal, the area of the petal is going to have limits of integration where cosine of 3 theta returns back to the pole. Well, that means that the angle measurement expression is pi over 2 plus pi n, or theta is equal to pi over 6 plus pi over 3n. So basically, it basically starts out here, if you were to start at theta is equal to 0, and it comes back to the pole at pi over 6. And then pi over 3 after that, and then pi over 3 after that, and then pi over 3 after that, and on and on and on and on and on. Okay, so if you back up to this negative, what you get is limits of integration that are going to be negative pi over 6 to pi over 6. And those are going to be our limits of integration for the whole petal. Now, let's go ahead and let's do just the area. Okay, let's do the area of the petal. The area of the petal, if we use our formula, is 1/2 integral negative pi over 6 to pi over 6 of cosine 3 theta squared d theta. Now, let's go ahead. We don't really have to do anything with that right now. Let's go ahead and let's formulate the area of region 2. Area of region 2 is going to be the area between the curves. And so it's going to be 1/2 negative pi over 9 to pi over 9. And we're going to take the outer one, okay, which is going to be our petal curve, minus our inner curve, which is just numerical. And so if that is the area of the petal and that is the area of region 2, then what we have is we basically can take one and subtract the other, and we're going to get that area. So let's go ahead and see what that looks like. Now, if we want to use our calculator, which we're going to, let's go ahead and go in, and let's go ahead and use the petal equation, the Rose equation for R1. Okay, so this right here, okay, we'll call this R1, and we'll call this R2. Since we're going to be using R1 more, that's the only reason I'm designating it as R1. So we have cosine of 3 theta, and then 1/2. Let's go back to our main screen. I know that the area of the petal is 1/2 the integral of negative pi over 6 to pi over 6 of just R1 squared. So just R1 squared and then d theta. Okay, let's go ahead and just store that in so we don't have to go grab it later. And then we're going to basically do, actually, if we just go up and grab this one, we can alter this one to be the same as this. So we'll alter the limits of integration. Okay, and then we will say minus R2, or I mean, it's numerical. You could just put 1/4, but R2 squared, and then enter. And so basically what we need is the area of the petal minus that area, and what we get is 0.102. Now, let's go ahead and take a look as to why we couldn't just do it just by finding region 1 by itself. And the reason is that you may not be able to see it when you're zoomed out, but when you zoom in real close, you notice that these bow out. So the only way to get the region, this region, without doing the subtraction that we did, is to actually do a sum of integrals. Because that middle portion right there, between those lines that I've just drawn, is simply a sector of a circle. But we have these, which are itty bitty slivers, and we happen to know that those happen between negative pi over 6 and pi over 9, and pi over 6, and I mean pi over 9 and pi over 6. So we already have the limits of integration to find those, but those little slivers are simply of the petal, whereas this little sliver right here is only of the circle. Now, of course, the circle can be done numerically, because if that's between pi over 9 and pi over 9, then this is 2 pi over 9. So we could do it just numerically, and because 2 pi over 9 is just your theta value. So the area of the sector is going to be equal to 1/2 2 pi over 9, okay, and then r squared, and then r squared. So that's 1/2 theta r squared. Well, r right here, of course, is 1/2 squared, and that winds up being 2 pi over 72, or pi over 36. Now, you could have used integrals as well, but why do that when it's just a circle? Okay. Now I need to actually find those little slivers right there, and let's just do one of them and then double it. So 2 times the area and let's use the positive limits of integration. That just winds up being a little bit easier. Pi over 9 to pi over 6 of basically, okay, basically we need negative pi over 6 to pi over 9, or pi over 9 to pi over 6 of that outer one. So that would be cosine squared, or cosine squared of 3 theta d theta. Now obviously those cancel out, and what we need then is we need to let's plug it into our calculator, and let's not toil with it for too long. So we remember that cosine 3 theta is in R1, okay? And so we come back here and we say, well, we've canceled the 2 and the 1/2 out, so let's just go for the integral from pi over 9 to pi over 6, and that was R1 squared d theta. So when I add that to pi over 36, I should get exactly the same thing, and I do. So if I add that to pi over 36, I get 0.102. Now, that's doable, but it requires actually zooming in and actually seeing that, and those are just really, really small slivers. But this was we basically arrived at that area by addition, whereas previously we did it by subtraction. Whichever one you want to do, don't worry about it. It's fine with me. Kind of, dealer's choice at that point. That brings us to the end of our discussion of area. The last video will be about arc length, and then I think you will have everything that you need for the test. As always, if you have any questions, please do shoot me an email.